using Tycho Brahe's observations, Kepler came up with or deduced a few results, which are generally called Kepler's laws. The first law was that he saw that all the planets moved around the sun in elliptical orbits, right, in such a way that the sun was at one of the foci of those orbits. So the top view of the solar system would look like this. So the second law is that the planets move faster when they're close to the sun and are slower when they move further away from the sun. Now, the same law is sometimes restated in a different manner. It is said that the aerial velocities of the planets is always constant. Now, what does that mean exactly? For that, let's just take the example of a planet that's moving in an elliptical orbit like this, and let's say this is the sun over here. Now, let's take the case where the planet is close to the sun. Okay. Now, what is the area swept by this planet in, let's say, one day? Now, in one day, let's say the planet moves from here to here. So the area swept will be this, right? So the area of this region is the area swept by the planet. Now, what the law says is that when, let's say, the planet comes to the other side, the area swept by the planet in the same time interval will be exactly the same. So for that to be true, the distance traversed by the planet has to be lesser, right? So that these two areas are exactly the same. So this implies that the distance traversed by the planet when it's close to the sun is greater, and the distance traversed by the planet when it's further away from the sun is lesser in the same time interval. Or in other words, the speed of the planet is greater when it's close to the sun and it's lesser when it's further away from the sun. So the third law says that the square of the time period of any two planets is always proportional to the cube of their semi-major axis. Now, if that sounds confusing, let me just explain. Now, if I take a planet that's going around in an orbit like this, the time period is obviously the time taken to complete one full revolution. Let's call it t. Now, what is the semi-major axis? For that, just consider the largest diameter is this, and half that length is what we call the semi-major axis. Now, let's call it r. Now, what Kepler found was that t squared is always proportional to r cube for any pair of planets. So till now, we've been looking only at the kids' version of the law of gravity. That is, we've only been talking about the magnitude of the force. But we know force is a vector quantity. It has a direction. So how do you represent that force? And how do you represent that direction? For that, what we use is unit vectors. For example, let's say I have 2 point masses, say 1 and 2, and you want to talk about the force that this point mass 2 is feeling from point mass 1. Right? You know that the magnitude will be g m1 m2 upon r squared, yes, but the direction will be in the direction of a unit vector in this direction. So f vector will be g m1 m2 divided by r squared into that unit vector. So now let me ask you an interesting question. Till now we've only been seeing a pair of point masses, or just 2 point masses. That's fine. But what if we have more than 2 point masses? Let's say we have 3 point masses, 1, 2, and 3. What is the force that this point mass experiences? Now, from the law of gravity, we know that both these point masses will attract this point mass, yes? Therefore, there will be 2 forces acting on this point mass. But what is the net force? Now, intuitively, you say, yes, it should be the vector sum of these 2 forces, right? Or the resultant of these 2 forces. But why exactly though? Why is it that the net force that this point mass feels should be the resultant of these 2 forces? Now think about it. Now, so the smart ones amongst you might say, see, we know that force is a vector. So to call something a vector quantity, it must follow the triangle law of vector addition. And we know that force is a vector, so therefore it must follow the triangle law of vector addition. If you say that, you're right, fine. But that's actually not the answer I'm looking for. The point I'm trying to make here is there is actually no logical inference from any of the laws that we know that says that when you have 2 forces acting, 2 forces of gravity or 2 gravitational forces of attraction that are acting on a mass, on a point mass, there's no law that says that the sum should be the resultant of these 2 vectors. But the thing is, we do find that this is the case. So in all our experiments, every time we observe multiple forces acting on a single point, we find that the net force is the resultant of all these forces. So therefore, we assume it to be true. Now, this principle is called the principle of superposition.